everybody. I'm happy to be here. Good morning, everyone. This is Informal Learning for developers, and I am Guillem Duran. And well, this talk will be an introduction to some of the fundamental principles of reinforcement learning. I would like everyone who's not familiar with the field to get an intuitive idea of what kind of problems is reinforcement learning trying to solve, what kind of tools do we have available in Python to tackle those kind of problems, and talk about some of the key concepts that will make us understand this field at least a bit better. After a brief introduction to some of the basic concepts of RL, I will talk about Python libraries for managing reinforcement learning environments. We will talk about some basic reinforcement learning algorithms, and then we will jump to the realm of deep reinforcement learning. And well, if there's time left, I'll talk about some things about the future of the field, or how I think this field is evolving. In the end, reinforcement learning is nothing more than a regular machine learning problem. But as in supervised learning, we have a training set and a test set and label data, which allow us to evaluate how our algorithms are performing. And in supervised learning, we had just a big data set with no labels, and we need to figure out the structure of our data. In reinforcement learning, things are a little bit different. Here, we do not have either the data set nor an objective function. So we need to build them both just by using what is called an environment and a reward system. But a proper explanation requires a lot of math. And there's no way you don't fall asleep if I spend 1 hour talking about mathematical formulas. So why don't we go on a quick adventure with Rick and Morty instead? From now on, this talk will be about video game Rick. Yeah, Rick turned himself into a video game again. It is the 3rd time it happened this week, and it actually turns out that every time he gets drunk, he does the same thing. And the only way to return him back to normal condition is by Morty playing video game Rick till the end and getting the maximum score. Of course, Morty is a bit tired of playing it, so he decided to code an algorithm so he can just plug video game Rick to a computer and let his algorithm take care of it. To automate the process, Morty started writing if clauses and handmade rules for each one of the levels of the video games, but the last. It turns out that this last level changes every time Rick turns into a video game. So kind of more generic approach will be required. And here's when reinforcement learning comes into play. In this last level, Rick can perform 6 different actions. He can move up, down, move right, move left, and he can pick up Morty or use his portal gun. But there's a few more things that worth noticing about this video game Rick. First, each time you play it, Rick will start in a random position in this 5x5 grid. There are some walls, which are not meant to be trespassed, and you can see that Rick can pick up Morty when he's over him. If he tries to do that, to do a pickup when he's not over Morty, or he tries to use his portal gun when he's not with Morty at the portal location, bad things will happen. But if he eventually gets to pick up Morty right and go with him to the portal and use his portal gun, then the game is solved and he returns back to normal condition. Well, now that we know the basic rules of the game, let's talk about the state space, which is a mathematical structure that represents all the different situations that we can find in a reinforcement learning environment. It is important to understand this concept because the structure of the state space will determine which kind of algorithms we can apply to solve a given environment. So, in this example, when a level starts, different things can happen. You can either go up and keep running wild, go down and crash your vehicle, move left and find some people to shoot, or go right and fight Morty. Of course, you can also try to use your portal gun or pick up Morty too early. But if you do that, bad things will happen. So it's not recommended. If we joined each one of the actions that we can choose with all the situations we can find, we would end up with something like this. This whole structure is what we call the state space, where each one of the images here are what is called in informal learning a state, which is just each one of the different situations that we can find in our environment. In this graph, the states represent the nodes, and the edges represent the actions that, if chosen, will take you from one situation or state to another one. You can see here in red what it is the initial state, which is where we start when we start playing video game rig. And here in green, you can see what is called the terminal state, which is the state that you reach once you have managed to finish video game rig. What is curious about this is that playing a video game and choosing a series of actions is equivalent of drawing a path inside the state space graph. In this slide, we can see different visual representations of what a state is. For example, we can use the state representation as the pixels that we can see in the screen, an RGB matrix. We could label each state and define it by a number, which represents a node in the state space graph. Or we, for example, could define a vector. And in this case, it would be like the first two coordinates, the x and y coordinates of rig in this 5x5 grid. The next one would be where Morty is located, and the last coordinate would correspond to where the portal is. All these different representations are somehow equivalent, and you can use either of them interchangeably, but it is important to know a bit about how the state space of your problem is structured before trying to tackle anything, and get an idea on how complex will all those connections in the state space graph be. Yep. Whoop. Moment. Well, so now that we know the mechanics of the game, we need to figure out a way to model our objective, which is teleporting home safe and returning rig back to normal. We will need a mechanism that allows us to numerically describe what we want to do, just the same way as scores work with video games. For example, like in the, going back to the former example, we can see that this is when rewards come into play. The reward, the reward is a number meant to indicate how good an action is. And if we want to choose a good reward distribution, it should comply with 3 different properties. First, the better the action, the better the reward you get for it. Bad actions should lead to lower rewards or even negative rewards. Also, a good reward distribution has high sensitivity, which means that rewards change frequently depending on how good an action is with respect to its alternatives. And finally, we have to remember that the reward is an instantaneous measure, which means that it's only giving a score to how good an action is at a given moment and not its long-term consequences. But unfortunately, real-world rewards suck. Most of the games do not comply with the three properties that I just said. Like, for example, in video game Rig, what you actually have is you get 20 points if you manage to win the game and return him back to normal. And you will get minus 10 points if you perform an illegal pickup or portal gun. But otherwise, you will only get a minus 1. Without taking, no matter what action you choose, or no matter how close are you to finishing the game. Another example when you can find a really sparse reward distribution is in the game of Go, when you actually do not get any kind of reward as to moving in your turn, but you only get 1 point if you manage to win the game, or minus 1 points if you lose. So yeah, real-world rewards can be very sparse, but also they can vary widely in scale. For example, in this Mario Bros. Example, you are not getting any reward when moving from one place to the other, but suddenly you can kill a lot of enemies and get a huge reward in just a few frames. This is pretty bad if you're trying to make a network converge, because it's basically just screwing up how you are trying to do the regression. But before keep talking about neural networks, first I want to show you what kind of environments could solve Morty in Python besides his video game rig. First, let's talk about OpenAI Gym, which is the most famous library for reinforcement learning algorithms in Python. And it has a really wide variety of different environments, and it pretty much has become a de facto standard in all this reinforcement learning field in Python. The thing is, the interface that it provides to very different kind of environments is always the same. What kind of environments do we have here? Well, let me, yep. No. For example, we have some of the problems from classic control theory. This is called the car pole balancing problem, which consists of what you see on balancing a pole in a car. You can also find toy test examples which are based on Markov decision processes, like this TATSI environment in which video game rig is based. Or also you can find environments where you have robot-like agents where you have to teach them different tasks, like jumping a wall or learning to walk. But the coolest thing about this is that you have a wide range of Atari video games available. And also there are two different ways of representing the states of these Atari video games, which are the RGB pixels from the screen or an NumPy array containing the RAM from the Atari emulator. How environments are used in OpenAI Gym. Okay, notes. First, you need to create your environment by using gym.make method and passing the name of the environment. You have to reset it in order to be able to start using it. And then you can do different things. First, you can display the environment if you want to see how your state looks like with the render method. And then you have to choose an action, either by using a reinforcement learning algorithm or by sampling it at random. When you have an action chosen, you just step the environment, and you get a 4-element tuple. The observation, which is the first element of this tuple, contains the information about how the state the environment is in is represented. You also get an integer describing the reward that you get for the last action that you performed, a Boolean describing if your state is terminal, and a dictionary containing additional information. For example, in Atari games, This info dictionary contains information about how many lives you have left. But moving to other packages, I showed you that OpenAI Gym can use robots and teach them to solve different tasks. But if you are into robot simulation, OpenAI RoboSchool is the library that you need to use. Why? Well, first, because instead of using the proprietary software Mujoko, it uses the open source physics engine PyBullet, and it also offers a more pleasing visual interface. For example, here you can see how you have different agents available to teach them different things. Here are competing one against each other. Or, for example, you have this cool version of Pong when you can have two players playing against each other. These are the Then OpenAI also offers the OpenAI Universe library, which is somehow as an extension of OpenAI Gym. What this library offers is first, it allows to run your environments inside a Docker container and access them using a VNC server. How many of you know what a Docker and VNC servers are? Well, basically, a Docker container is some kind of virtual machine which is meant to isolate your applications, and the VNC is a protocol for remote desktop controlling and visualization. So basically what this is offering you is a way to isolate your environments and deploy them remotely so you can play over the network or locally, because it also offers the capability of working with different environments in parallel. So if you need to scale your algorithms and make them bigger, OpenAI Universe is your solution. So furthermore, this thing of using the VNC server makes it available to use a wider range of environments than OpenAI Gym. So it also offers different things like these Flash games, for example. The only drawback of this library is that if you're using the VNC server, it works in real time. So you need to be quick when choosing actions, because the environment will keep running without waiting for you to input an action. Now let's talk about this Internetvana coach library, which has been released very recently, but I find it pretty cool, because first, it's compatible with all the other libraries which uses the OpenAI Gym interface. Like here, for example, we have a PyBullet robot, which is where you need to make him walk. Or you have a task which consists in picking up health packages in the video game Doom. But the coolest thing about Coach is that you also have a wide range of different algorithms available to test on the environments, and also a visual interface with dashboards that allow you to debug and see how your agents are performing. If we moved to the DeepMind libraries for reinforcement learning, first we should talk about Lab, which is a library where you need to teach this kind of ball to perform different tasks. For example, here you have this kind of maze, which is in 3D, and you get the pixels that you're seeing each time. And you need to learn to navigate it and earn more reward, actually. I mean, it can seem like a pretty simple task, but the fact that this is in 3D and you can move the camera around and you have all these colors and such makes it actually a really difficult task to solve. So when you don't have a big GPU, you shouldn't even try. But in case you want to go really hardcore, you can always try Starcraft II. Here, your environment is Starcraft II, the Starcraft II game. I mean, playing the whole game is extremely difficult, so it only offers some kind of mini games based on the Starcraft engine. For example, you can solve different tasks like following a beacon, creating different units, or gathering resources. By the way, if you install this and you try to solve an environment and you fail miserably, do not feel bad. I mean, this is a sentence which is hidden inside the Starcraft II paper from Google DeepMind, which basically says, the results of our baseline agents demonstrate that even relatively simple minigames present interesting challenges, which we hope will inspire new research. Well, this, in the language of researchers, basically means that they are completely lost. So do not worry about it, because right now, Starcraft is so difficult that no one can tackle it. Actually, I bet it with my coworkers that they won't be able to solve, to beat a newbie player in less than 5 years. Let's see. They disagree with me, so let's wait and see who's right. Well, this is all the kind of environments that you can find in Python. But now let's move to different algorithms and how we could solve these environments. Remember that, as I said before, reinforcement learning basically consists on 2 tasks. First, we need to manage to generate a data set, and then we need to manage to build a target function. So we can apply everything we know from machine learning with a created data set. The first algorithm I will explain is the value iteration algorithm, in where the data generation process is pretty simple. You just need to take every state and every action available into account. Pure iteration, brute force. And in order to build your target function, we will build a table which is called the value function. But what's a value function? Okay. It is a function that assigns a scalar to each one of the states. And this scalar works at some sort of long-term reward. We said the rewards were something which was an instantaneous score. But here, when we try to build this value function, what we're trying to do is assign a long-term reward to each one of the states. So basically, this is building a target function for states and not actions. The problem is that we only have instantaneous reward, and they are assigned to actions, not even states. So we need to find a way to transform this reward mechanism, which is instantaneous, into something that serves our purpose of finding a target function. I will show you a few animations on how this value iteration algorithm works, but first, let me show you the code, okay? It basically consists in iterating through each one of the states and the actions. And for each one of the states, we need to see which will be the states that are accessible from a given moment. I mean, if I'm here, what can I do next? Well, for each one of that states, we will get its value function, and we will update our value function with the maximum value function that we can access in the next step, plus the reward to get there. Sounds a bit complicated, but it actually is more simple than it looks like, okay? We start with all the nodes and value functions at 0, and we can see here, for example, like in the video game rig environment, that we have a lot of crappy decisions, we get crappy rewards, but 1, which gives us 10 points from D to F. How do we build our value function from this? Okay, we start iterating. Whoop, or not. We start here. Okay, first iteration. We need to look all the states available and get the maximum value function available plus the reward to get there. If each one of the nodes are labeled with 0, we only take into account the rewards to get to a given node. So in the end, D would see 10 points to go to F, and F would see 10 points to go to D. So we update the value function. Now we iterate again through all the states and see how this value function is propagating. Because now, when this was formerly 0, it looks its neighbor and see that it has 10 points here, which is the maximum. 10 points minus 1, which is the reward to get there. You end up with 9 points here. Also happens here and also happens here. But as you had before, 10 points here and here. Now, when you look at the maximum score you can get, you see 10 points plus the 10 points of the 10 reward points to get to the other place. So you sum them up. You keep iterating, and you see how all the rewards are propagating through your state space. Let me show you an animation on the entire state space of video game rig. Here you can see this is the terminal state, and this is colored according to the value function for each one of the states, ranging from blue to low value function to red to indicate a high value of a value function. Here you can see how everything is propagating and how all the nodes are increasing its value function at each iteration. But I'm showing the absolute value, and maybe it's more clearer. Oh. Here I'm using the whole color map for each one of the iterations, so you can see how everything is spreading in, and the value function relative to the other nodes in the graph. But this kind of rainbow color map, I'm not sure if it's the most clear option that we can find, so I will show it the same thing in green. Here we have our terminal state, and we initialize everything at 0. And each time we iterate, we can see how this value function is propagating through all the graph. What are we doing here? Okay, what we will end up is some kind of measure of how far are you from the terminal state. I mean, if you're always winning, you are at the best position you can be. And the farther you are from the terminal state, in theory, the worse is your position. So this is the idea, what this algorithm is trying to capture. It's building from an instantaneous reward mechanism, something that can give you long-term information on how good a state is. Good and bad things about this algorithm. Well, good things are that given you satisfy a few constraints, it can solve any kind of reinforcement learning problem. But sadly, well, let's talk about the constraints. First, little detail, it requires full knowledge of the entire state space. This means that you need to be able beforehand to know all the rewards that you can get for taking each one of the actions. And you need to be able to iterate many, many times across the entire state space, which is pretty easy if you only have like 100 different states, but typical video games can have more states than atoms in the universe, so it could take a while to make it converge. Actually, the first time Morty tried to apply value iteration to solve video game rig, he found out that he couldn't do it because it turns out that video game rig has fog of war, which basically means that we do not have a prior knowledge about the state before visiting it, nor the rewards about the actions that we will have available at that state before choosing them. So basically what happens is that we cannot iterate backwards what we don't know, and like in games like Video Game Rig, where you only get one significant reward, which is worth propagating back, you find yourself completely blind if you do not have access to the whole state space. Luckily, in order to handle the fog of war effect, the eLearning algorithm was invented. In eLearning, we follow the same principles as in value iteration, but as we cannot have access to every possible state, we will use what is called an exploration policy, which is basically a way to move around the state space when you cannot see it entirely. We will keep storing all the target or Q-value function in a table, so we don't have to worry by now about machine learning models. So this Q-value function, which is somehow like a value function, but instead of assigning a long-term reward to each one of the states, it's assigning to each one of the actions. I mean, the reward is something instantaneous, and the Q value is a score for the rewards on how good is this action at the long term. You can see that the idea is pretty much the same, but instead of iterating the entire graph, you just have to choose an action using your exploration policy, step your environment, and update your Q table. Then move around the environment and keep iterating. Well, the saying here is that basically what we're doing is iterating the entire state space with what is called an exploration policy. The epsilon greedy policy is the more used exploration policy that there's out there. I mean, almost everyone uses it with few variations, and it consists on the following. You throw a biased coin, and in case you get heads, you move it random. If you get tails, you look at your Q-value table and choose the action with the highest Q-value. This means that this epsilon parameter is somehow a measure of how much you trust your Q table. If it's big, you will pretty much move it random through the state space. And if it's low, you will always trust your model, which is the Q-value table which assigns scores to each one of the actions. Well, in this case, the way that we update our Q-value function is pretty much the same as we did with the value function, but for actions instead of states. We have a current value, which is our table now, and we get a learned value, which is the Q value that we could get in the next state. So pretty much what we do here is we do a weighted update, so we cannot forget completely the old value, and we added the reward and a discounted expectation over what you can get in the future. Q-learning, pros and cons. Well, if we think about it, is that if we manage to make enough steps in our environment, choosing always the action with the highest Q value should result in a perfect game. And thanks to this exploration policy trick and the weighted updates, we get somehow to manage this fog of war effect and be able to still achieve something without having to iterate through all the state space. And, well, of course, this is solved at the cost of introducing new parameters, because now you are relying on your exploration policy, in your discount factors, and how you're weighting your new values against the old ones. But I think that the worst thing about this algorithm is that the Q table can get extremely large real quickly, because it has as many rows as states there are, and as many columns as actions available. So when those tables get too large, the only thing that we can do about it is using neural networks to approximate the Q-value function or the value function for the states. By using neural networks, we can virtually tackle any reinforcement learning environment. So in theory, say it twice, we don't need to care about the fog of war effect or the state space complexity. But now we need to care about how we will train this network, because we are not only building a target function and a dataset from the environment, because now we also need to define a training strategy and a loss function for our network. So you are trading somehow scalability for parameters and complexity. So to train it in formal learning, we need some kind of a paradigm shift. To do so, we need to define a proper loss function and a training methodology, like pretty much in any other machine learning problem. But it's important to note that neural nets here just act as black boxes. Instead of tables, we have a neural net. But we do not have any idea of what's happening inside them or why they even work. So from now on, I will represent them using a mystics box, which is a super cool device that when you press the button, it summons Mr. Mystics, which is this kind of blue fella, which will make all your requests come true, and then will disappear. Well, as you can see here, deep Q-learning is pretty much the same as regular Q-learning, but in this case, you have a neural net instead of a table, and you are not propagating backward the rewards, but minimizing an objective function to make your network learn. So the approach for the Q-learning is pretty much the same as in Q-learning, except for in the Q-value update phase, where we had a weighted sum for the old value and the learned value. Here, what we have is a loss function, where instead of weighting both of the two values that we had before, now you are subtracting them and trying to minimize the loss using a Hoover loss or whatever loss that you like. Well, what it happens also is that it's increasing your complexity. I mean, now you have to work with tensors, you need to define a training strategy, make batches, and blah, blah, blah. And also there's like 20 different variants of deep Q-learning, each one doing things a bit different. But what I want you to take from here is that, and to remember, is that it's based always in the same principle of propagating backwards the reward. I mean, half of the informal learning is just propagating rewards backwards. So as long as you have this really clear in your mind, no matter the weird variant that you can find, you will always understand what this is trying to do. Well, now that we have surrendered to the deep learning, why don't we just focus on applying backpropagation? I mean, we're still trying to do something which was propagating backwards a reward and trying to make an algorithm converge, but instead of tables, using neural nets. So why don't we just forget about this thing of propagating rewards and attack reinforcement learning as if it was a regular machine learning problem? So from now on, what we will have is still a data generation process which relies on how we choose our exploration policy, and a target function which will be called advantage. which will be calculated as some kind of gradient of our network. Before going on, a quick recap. We have talked about three functions, which are the value function, the Q value, and now I'm going to explain this advantage function. I mean, they all do pretty much the same, which is trying to get an idea of the long-term consequences of choosing an action or being in a state. The difference is that the value function is applied to states, which are the nodes in the state space graph. The Q value function is applied to actions, which were the edges, and this is exactly the same, but instead of using it for rewards, for actions or states, you are using this directly as a gradient. So this is how policy grading works. On the right, you have what I just said, the data generation process, and your target function definition, which in this case, I'll tell you, it's called advantage. So given that you're able to figure out a way to move around the state space and to calculate the eventual reward or long-term consequences of the actions that you're choosing, what you can do is use this eventual reward and put it here in the gradient. I mean, in this case, you have an observation for your environment, you pass it to your system of statistics, and you get probabilities for each one of the actions. You can sample them, you can apply a greedy policy, do whatever you want, and move around. And eventually, you will be able to estimate which was the reward that you get from here. If you just put it here as a gradient, what you're doing is discouraging taking this action. I mean, your reward function will be a distribution over your actions, which will be encouraging or discouraging taking a given action. How you do that with your advantage function is what will make your algorithm work or not. So the way you sample the actions and the way you calculate your rewards, either by, most of people, this advantage function, what they do is they play a whole game and then they go backwards and say, okay, I did that, I took that action, I kept playing for whatever number of moves, and I got that reward. So they just discount that reward and use the discounted expectations of what I will get as a sort of direct gradient. If the reward that you get is negative, you are discouraging their actions and moving away from, moving your parameters away from that. Or if you have a really positive action, what you're doing is trying to encourage a lot the network to learn to output that action. Yep. So everything here is just regular deep learning. The cool things about reinforcement learning are here when you choose how you move through your state space, or when you're here trying to calculate your advantage function. But everything else is just the same as you do in deep learning. But I must warn you, all the tools have its dark side. And reinforcement learning, well, deep reinforcement learning has a pretty nasty one. Reinforcement learning is a field with so much hype that about every 3 months it's published some paper which is promising to be revolutionary. But the truth is that all the core concepts of this discipline are decades old. I mean, what we're doing now is just waiting for Moore's law to scale and have bigger GPUs so we can tackle more problems. And well, remember that each time that you're increasing the size of your network or trading a table for a deep net, what you're actually doing is hiding your ignorance behind a wall of metaparameters. So in theory, we all know that all the networks can converge, but well, you may end up with a lot of metaparameters. Actually, this is not even an exhaustive list. How you explore your state space, how you choose your optimizer for the network, your advantage function, the architecture of the network, different optimization parameters such as the laning rate, momentum, the batch size, how you're updating your gradients with respect on how you generate data, if you are clipping losses or gradients, or even the random seeds that you use can have a huge effect on how your algorithm will perform. Actually, there's a paper out there which says that you can find about 40% variance in your results depending just on the random seed that you choose. So yeah, pretty nasty. Oh. So be aware that even though in theory deep nets can approximate any function, they are black boxes that we do not understand. So if you end up stacking them and hoping for the best, it's really easy to become a prisoner of your own tools. So here are a few things that turn out to be useful to remember when trying to tackle a reinforcement learning problem. First, it's important to know that we have almost no control on how we're learning the features. I mean, for example, when using policy gradient, we are just encouraging or discouraging actions, but we are not caring about how the network is learning to discern about your preferences. So in that sense, we are kind of blind. And 2 points come somehow together. We are just using an exploration policy, which is basically moving either at random or with a model which is not trained yet, around the state space. And what we are doing is what we have already found, we can learn from it, but things such as imagination and planning were taboo in this field until very recently. So in the end, you're basically learning from memory. You have no way to plan or imagine the future in order to find better paths around the state space and so forth. And do not forget that as long as you are trying to optimize a gradient, you will end up in a local minima, which means that even though your network is converging and you're doing everything right, maybe the local minima when you are stuck is not good enough to get the reward that you wanted. So, sorry. Good thing is that there are a lot of dirty tricks that happen to work also in this field that also work in deep learning, such as clipping the lives and the rewards, clipping gradients, which basically means when you are clipping something is that you are trading information contained in your state space for a smoother and easier to optimize loss function. So even though it can improve convergence, if you do something like clipping the scores, you are limiting the maximum performance of your model. For example, if you clip the scores from -1 to +1, it would be the same thing for the network to do something that gives you 1 point or do something that gives you 100. So you're losing information there. What people do in order to make the networks converge faster is using what is called a memory. I mean, you play like 1,000 games and you store all the images in a memory, and then you just do sample batches from there in order to decorrelate a bit the samples and avoid overfitting. Of course, dirty tricks like batch normalization, using regularization penalties, or any kind of computer vision trick that happened to work in deep learning, it will also work in deep reinforcement learning. Or at least it should improve a bit your results. So now that we've seen a few principles that turn out to be repeated over and over with actually pretty little variation, it's time to take a step back and think about what we're doing. Nowadays, Q-value methods are pretty dead. They have been published a lot of variations and they have been tried a lot, but it turns out that policy gradient-based methods work pretty much better always. But even though research is slightly moving forward, there's a few things worth mentioning. I'm not really sure of the real utility of some of the research that is being published. For example, here, you can see some figures from the Starcraft II paper from Google DeepMind, where you can see the performance on different simple tasks. What they did here is that they play 100 rounds, and they colored like more strongly the best result that they got. But if you take a closer look, you can look that in the appendix if you want. It's included in the list of papers and such. You see that tasks like defeat Zerglings and Vanillings, there are just 2 times where this algorithm performed well, and let me nope. Well, not working. Well, what I wanted to say is that out of 10 times, there were 98 times where this algorithm didn't accomplish anything at all. And somehow, 2 out of 10, they did something. But if you look at the gray part of these graphics, you can see that the variation is extremely large. So basically, this means that either you have a really big GPU and computing and you're Google and can make the experiments run thousands of times, or you have to be lucky, basically. Because you can see here there's so much variation that a normal person doing reinforcement learning stuff at their home won't be able to mimic, to reproduce these results unless he's able to do the same calculations as Google did 100 times and take their best run. As a final remark, I wanted to show you this image from the PhD thesis of Shane Leck about reinforcement learning algorithms. Let me read the caption in case you don't see it. Basically says,
you're about to run out of time.
I know. It's the last slide.
Okay, good. Very good.
Well, it basically says that we are in this lower region with weak provable algorithms. I mean, this guy, what he did is he found 2 theorems. One telling you that there is no simple algorithm that performs super well, but what you can prove has a limited performance. So everyone is trying to prove the algorithms and work based on solid math. But what actually this guy is saying is that if we are able to find a really cool algorithm that works extremely good and works better than anything else, we will probably won't be able to prove that it works better than the things that we have available. So as it's almost time, I will let you ask me questions and I will show you. Oh, nope. Well, let's go to the Q&A session, and meanwhile I will just run these algorithms here to see what reinforcement learning can accomplish. If I manage to make it work.
Okay. Can I start?
Well,
yeah. Okay. Actually, what you show, basically, even with Q-learning or deep learning with the deep networks, you still more or less start from moving from random. What if you know something about the problem? I mean, is there some transition? Well, in the search algorithm, you have just the extra algorithm, or you have a star algorithm if you have some prior hypothesis about your state space, how you can reach the final state. Is there anything similar here?
Well, course, any information that you have about the state space beforehand, you can use it either by defining custom rewards in order to embed your priors in your reward distribution, or you could do something like pretaining a model in some other task and try to start instead from random weights from something which is pre-trained. I mean, everything that you have in mind can be potentially useful. Given that you have no idea at first, how you define your priors will have a strong influence in what you get. So if you're able to define some good priors because you have knowledge of that specific environment, you can achieve better rewards.
But how you incorporate this into...
For example, Pac-Man, Microsoft managed to get the maximum possible score in Pac-Man, and what they did was they created 500 different deep learning models, and they trained each model to solve a really specific thing, like run away from a ghost, avoid being dead, try to eat the more fruits you can, and getting all this handwritten knowledge embedded in a network. I mean, they trained 500 different networks to solve really silly things and then combine them all together so they could beat Pac-Man. I mean, this is almost brute force and totally an overkill, but it shows you how you can embed your priors in almost any kind of task.
But the idea is to avoid brute force as much as possible.
Yeah, that's the problem. I mean, no one has any idea on how to do that.
Okay. Okay, thank you.
Thank you for your talk. Could you speak a little about if there are any approaches worthwhile to look at for extrapolating from experience or memory to augment the reinforcement learning with something that is based not just on memory but some
imagination or planning. Okay. Yeah. There's this technique which is called Monte Carlo tree search. What they are trying to do is, I'm in this state, so as I have access to all the decisions and such, I will just search around where am I, like in Go. I will play a lot of moves from this position, see where they get me, and once I have a full tree of possible movements explored, let's choose where I should get. I mean, it's like trying to play forward the game, then go backwards and say, okay, if I'm in this position and I know that from here I can get to all this region, where should I move now? So they are trying to explore beforehand the state space, but the methods are not that good. I mean, they work, they manage to train AlphaGo and beat all the Go players, all the Go human players in the world, but there's still a lot of research to do in that areas.
I'm sorry if I misunderstood, but what's the conceptual difference from algorithm like alpha-beta search or min-max?
No, actually, there are variants of almost the same concept. I mean, you can also use that instead of Monte Carlo tree search.
I see. Thanks.
Actually, most of the variants of deep learning, of DQ learning, are about trying to use these techniques to improve the scalability of the algorithms.